Hey everybody, welcome back. How's it going? So again, last time we looked at a lot of NumPy stuff, and if you didn't understand that, that's totally okay because we're going to go through and over it anyway. Today, I really hope that you understand at least what I say in this video, and of course there's a lot more behind the scenes as to what's really going on in a computer and whatnot, but at least understand what I say in this video before you proceed, please. So we're talking about today vectorization or parallelization, okay? And so the main idea is that we want computers, and just logically, we want stuff to happen kind of at the same time rather than one at a time. Okay, and that's for speed purposes. So in a computer, we can kind of do parallel computing, as in we can kind of make stuff happen at the same time. It's a large topic, but let me explain with an example why a big reason why we're using NumPy and why we're going to change all of our stuff to using NumPy and parallelization stuff in the future. Say, for example, in math, we had the vector a is equal to 1, 2, 3. And I wanted you to implement the operation. I wanted you to do a plus 1. So I wanted you to calculate or return the vector of a plus 1, which is going to be 2, and then 3, and then 4. Okay, we need to do that computation though. So the big difference between vectorization and normal, or also working with Python lists, not vectorizing, versus NumPy vectorizing, is that when we do normal list, so say that we are given a is equal to the Python list of 1, 2, 3, and if we were to implement the operation a plus 1, or really anything, the point is anything where we're doing anything to multiple components of the vector and generally all components of the vector or matrices, we would do in this case, we would say for something like we'd get maybe a return list. So we'd get a return a, so what we'd get at the end is equal to this empty list. So for now we have nothing. And then we would say for element or component in A, okay, so we're good. First time it's 1, then 2, then 3. We would want to do return A dot append with A plus 1. Okay, so that's how you would compute this normally. If you were given a Python list, you actually have to go through one at a time and say, no, you're plus 1, then you're plus 1, then you're plus 1. So this is bad. Okay, I'm going to give this a red X. We really don't want to do this. What we do want to do, and I'm going to give it a green check mark after because this is really important, is we want to pretty much all at once as well as we can, and computers can't do everything all at once. But if instead we wrote this with NumPy vectors, it would more so do something along the lines of, okay, we had a is equal to the NumPy dot array of, say, 1, 2, 3. Okay, and I know that, no, sorry, that got cut off a little bit. I'll zoom out a bit. And I know that I'm not using the column vector notation like before. It doesn't really matter in this case. So say I have the array as 1, 2, 3, and then I wanted to add 1 to each element. Well, as you saw, I can do this with just, I'll just say return a to keep the same variable as before. Return a is equal to a plus 1. And all sorts of similar stuff like that, and pretty much everything in NumPy, unless you write it with a for loop, you are going to pretty much simulate the operation of we add 1 to each of these things at pretty much the same time. So what this says is it says, oh, okay, I want return a to be just add 1 to everything. Don't first go through add 1 to the first thing, then the second thing, then the third thing. Do it all in one go. Vectorize this operation so that we are returned. This again would be, well, I don't need to write it out. It would be the same thing, but a NumPy array of 2, 3, 4. And it's a lot faster for a computer to do it this way. It's also just easier for us to write it, which is nice. But the main point is the speed trade-off. It's so much faster for a computer to, every time we do a for loop, you explicitly have to go through. No, you're saying, I must go the first thing, then the second thing, then the third thing. With a vectorized approach, and now I'll give it a check mark, is with the vectorizing, it's trying to do it all in one go as much as it can. So maybe it can't do everything all at once, but it's going to do as much as it can and be so much faster. And this is just an example when we have three things, three elements, but imagine if we had a million items, then you would have to go through, first the first thing, then the second thing, and the third thing. But if you can parallelize a million things, then it's like, okay, boom, let's do all of that as much as we can in one go, and then we're going to get the same result. It might look like a slightly different object. It's a NumPy array instead of a Python list or whatever. But this is the main reason we're using NumPy, is because it's so much faster and it does this vectorization operation, whereas Python lists just really don't. Okay, and there's other sorts of libraries where you can make them do that, but we don't really care about that. NumPy is great. So I hope that made sense as a rough idea what's going on, and I'll see you in the next video where we start using NumPy to do some cool stuff.